All right, so this will be a worked example that comes from ACE Physics Syllabus Code 9702, paper 22 from May, June 2018. You can see that it's the first question from that paper. It wants us to A, define force. Force is defined as the rate of change of momentum. When we study momentum in more detail, we'll re-examine Newton's laws through the lens of momentum. But in physics, we agree that the definition of force is this one. There are different correct ways to think about force. When you're first introduced to force in elementary school, you're typically taught that a force is a push or a pull, and that's true. Like even gravitational forces, that's a type of force. It can be thought of as like a pull, right? Like the Earth's gravity pulling you down. But that's not a very precise definition. We want this precise definition. Force is the rate of change of momentum. That will become F equals ma when we have an object that has constant mass. And so when we first introduce Newton's second law, we say for a body of constant mass, the acceleration is directly proportional to the net force, or the quantities force, mass, and acceleration are related by the equation F equals ma. That's another way to think about Newton's second law, or what a force is. It's equal to mass times acceleration, but that's not always going to be true because we could have situations where the mass of the object is changing. And so this more accurately captures how either the mass or the velocity of the object could be changing. Momentum is the product of mass and velocity. And again, we'll study that in more detail. At this point of the year, you want to have this just sort of in your notes as the definition of force. If you're ever asked to define force, don't say a push or a pull, don't say F equals ma, say the rate of change of momentum. Mathematically, that looks like, force equals the change in momentum over the change in time. Delta P over delta T. State the SI base units of force. Does anybody remember what that is? The SI derived unit of force is a Newton. But what is a Newton equal to? In other words, if you said Newton, then you remembered the SI unit of force, but not the base units. What are the base units? Kilogram meter per second squared. That's what a Newton really is in terms of the base units. A Newton is a kilogram meter per second squared. So that's what you would want to have down as your answer. This is a derived unit. These are all base units. And where does this come from? Again, you could use this definition of force to get to that. It will work. But you could also use, F equals ma, the more familiar one, and just kilograms of mass times meters per second squared of acceleration. That's why in Newton, the unit of force is a kilogram meter per second squared, base units. Now we've got part C, which says the force F between 2 point charges is given by F equals Q1, Q2 over 4 pi r squared epsilon, where Q1 and Q2 are the charges, r is the distance between the charges, epsilon is a constant that depends on the medium between the charges, and we want to use the above expression to determine the base units of epsilon. So this is a law in physics called Coulomb's law. Charles Coulomb was a scientist in the 1700s who was one of the first people to really study electricity. And so the unit of charge, I'm going to write it here, Q1 and Q2 are charges measured in, we honor Charles Coulomb by naming the unit of charge after him, measured in Coulomb's C, okay? So that's the unit of charge in physics. It's not a base unit, right? Because it's not one of those 7 quantities that we listed as the 7 base units. So remember that this is the type of question where we've got to sort of puzzle together the answer. We've got to know everything else in this equation besides the thing epsilon they ask us to solve for, which is that variable there in the denominator. All right, I'm going to start by writing out the quantities that are related by equation. So I have here the force is equal to Q1 times Q2 over 4 pi r squared epsilon. Does anybody know the base units of the left side of this equation? The base units of force. Only there were a place to reference to know that. Some students are saying, well, this is part C, and then in part B, we actually answered that. So that is helpful down here now. Okay, force is, so these are quantities, right? Force is a quantity, but measured in what units? Force measured in kilogram meters per second squared. And again, while I'm working, I prefer to work with a positive exponent down here in the denominator rather than writing it like that with a negative index. But you can work with, negative exponents if you want to. Good practice. Question?
What does it say below the Q1 and Q2?
It says 4 pi r squared epsilon. Let me zoom in and enhance. And I'm trying to sort of navigate between two different projectors here. And really, I'm recording this to put it up on YouTube. So I care more about like this projector than you guys here. Because you guys can look it up on YouTube too. Like you don't want the quality of that stuff. But that's fine. I'm more than happy to field the questions as you're taking notes here in class. All right, so we got the left side figured out. Now we just got to figure out the right side. That shouldn't be too hard. Does anybody know the unit of charge? Now, the question wasn't friendly enough to give that to you, but I was, right? So I wrote it out here, measured in coulombs, but that's not a base unit, right? We're trying to get this down to the base units. And so what we really need is an equation that we're going to eventually get to when we study electricity. The intensity of electrical current is the charge per time. Like if you're looking at the water flow in a river, you're counting like how many water molecules per time. That's like the current of the river. And it's the same thing with electrical current. You're just counting charges instead of water molecules. So the rate of flow of charge is current. It's measured in amps. So really we could rewrite this as charge equals current times time. Charge is current times time. And we'll study this in more detail, a few weeks from now when we finish mechanics and start studying electromagnetism. And so these are quantities, right? Q is a quantity charge, I is a quantity current, T is a quantity time. What are the units, though, that we measure these things in? So a coulomb of charge is equal to, does anybody know the unit for current? Voltage is actually the energy per charge. So voltage has something to do with how much energy is in each charge. Like a 9-volt battery puts 9 joules of energy for every coulomb of charge that flows around a circuit. So voltage is not in this equation, but we will study voltage, but that's not the unit of current. So voltage is a quantity, and we measure it in volts. It's my favorite one because it's like, what do we measure voltage in? Volts? Why can't they all be like that? Voltage measured in volts, right? So this one is current measured in amps. Amps of current. It's one of the base units. So too is the base unit for time is seconds. So a coulomb of charge is really an amp second. It's an amp times a second. When you go to buy a battery, you might look up how many amp hours are in the battery. Amp hours is really telling you the charge in the battery, right? Because a current times a time is a charge. So these are all units here. A coulomb is an amp second. So on the right side of this, I see I've got coulombs of charge times coulombs of charge. But what I really have is like this squared. So in the numerator, I've got amp seconds for that charge. And then, you could write it again, or you could put a squared there. However you want to show that like each one of these charges has units of amp seconds. These are base units, right? I'm doing everything in base units. I could have written C squared and then substituted that in. Okay. Over 4 and pi are just numbers. They don't have units. Okay, so we don't need to add any units down here associated with 4 and pi. What about r squared? Let me know the units of r squared, where r is the distance between the charges. Say it again. Meters. And it's squared, so it's going to be meters squared. This is what we call an inverse square law, and it very much resembles Newton's law of gravity. So Newton's law of gravity is mass 1 times mass 2 over 4 pi r squared. I'm sorry, just over r squared. There's no 4 pi in it. Mass 1 times mass 2 over r squared. So it also goes as inversely proportional to the separation distance. The further away charges are, the weaker the force is between them, right? Because it's in the denominator. If you separate these two charges by twice the distance, the force drops by a factor of 4. If you separate them by 3 times the distance, the force drops by a factor of 9, and so on. So it goes as the square of the separation distance, inversely proportional. So we've got r taken care of, and now we need epsilon. And remember that epsilon is going to be our unknown there. It's the thing that we got to plug in whatever we need to down here in the denominator to make this side equal to that side. So we have homogeneity. So I'm going to rewrite this as kilogram meters per second squared on the left side equal to amp squared second squared over meters squared. And remember that epsilon is in the denominator. Like whatever I plug in, I'm plugging in the denominator. But that doesn't mean I couldn't have like a denominator in the denominator. Like there couldn't be units of epsilon that's like, something per whatever, but the denominator of the denominator is the numerator. The denominator of the denominator is the numerator. So I want to kind of plug in whatever I need to in these brackets, keeping in mind that it's really in the denominator, okay, before I report my final answer. And remember, so everything I plug in, I'm going to start down here in the denominator, plugging it in for epsilon, and then I'll say like, oh, if I need it in the numerator, then it's like that per this, right? It's like anything I put up here in the numerator is really like in the denominator of epsilon. All right, so what do I want to include with epsilon down here? Let's start with the left side. On the left side of this, we've got kilograms, but we don't have any kilograms over here. So we need one. We need kilograms. The only place I can add things in is for epsilon because it's the one they asked me to determine. Everything else I have to just know. So I need kilograms up here in the numerator. And so whatever the units are of epsilon, it's something per kilogram. Okay, it has to be per kilogram because that's how I'm going to end up with kilograms up here in the numerator to make it equal. So I know whatever epsilon is, it's something per kilogram. Okay. How about the meters? I need meters in the numerator. Right now I've got meters squared in the denominator. Right? I have meters squared already from this value of r squared, but I need to get rid of them, and I need to have one left over up here in the numerator so that I get kilogram meters when I'm done. So how many meters go here in the numerator? If I put meters squared, I'd cancel out this, but then I need one more, right? So I actually need meters cubed. If I put meters cubed up here, I'll cancel out those two, and I'll be left with the one that I need. So far, so good. I got kilogram meters. But I need a per second squared, and I don't need any amps. So how do I get rid of these amps? Amps squared. The units of epsilon must be amps squared per kilogram per meter cubed so far. Because this is how we'll cancel out those amps squared, putting it down there. So now the amps squared cancel, the meters squared cancel, I'm left with 1 meter, I'm left with a kilogram, good. But now I need a second squared in the denominator. All I've got is a second squared in the numerator, coming from these charges, right? Amp second is a coulomb of charge. So how many seconds do I need and where do I need them? If I were to just write this out right now, what would I have? I'd cancel out the amp squared. I'd have kilogram meters second squared, not kilogram meters per second squared. So I need to get rid of those seconds squared in the numerator. In the denominator down here, right? If you had seconds to the 4th power down here, You'll cancel out those two, and you'll have 2 left over, which we need. Now, here's the tricky part. And I'll show you the error that I made this morning, or maybe I won't. Maybe I won't show you my errors. So here I am at the end of first block, rushing through the end of this calculation, doing the same working we just did, and then go, okay, good, kilogram, meters, that's wrong physics. Sad face. Remember, it's in the denominator already. I should have reported this not like kilogram meters cubed per amp squared second to the 4th, but rather this way. Amp squared seconds to the 4th, right? Per kilogram per meter cubed, right? Because those things were actually in the denominator of this denominator. That's why they showed it back there in the numerator. That's the correct answer. Let's just be careful and get it right for ourselves. So here we've got the amp squared, the amp squared are gone, the seconds squared are gone, and the meters squared are gone. So we have the correct units. Kilogram meters per second squared equals kilogram meters per second squared, okay? We end up getting everything is homogeneous if we plug in this for epsilon. And so what is all this for epsilon? Remember, epsilon's down here in the denominator, so it's amps squared seconds to the 4th per kilogram per meter cubed. And that nightmare of an answer is like the toughest problem you'll ever see when it comes to base units. Like this really, like it never gets harder than this. Okay, so if you were like, well, that was really confusing. Well, it kind of should be. This is kind of a pretty tricky one, and we're first learning it, and we haven't even really been introduced to the physics we need to make sense of these. And so really, it's kind of a good preview to show you that, yes, the idea of base units is such a foundational one, they'll assess you on it in the first question. Okay, but they're expecting you to know all your physics, like you remember what a coulomb of charge is, because if you, it's not friendly enough to remind you, oh yeah, it's measured in coulombs, which by the way is an amp second. Remember this equation. You have to know that equation so that you can make the correct substitutions here for coulombs. Because if you don't have this, there's really no way forward, right? So you'll just eventually hit a brick wall where you're like, yep, I don't know that physics. That's what I need to know. I wish they would have defined charge for me or given me an equation for it. All right, because the only way to actually get to that correct answer is to sort of know it all there. And then be very careful. There's plenty of chances to make mistakes, especially when you're, being rushed to dismiss class early. That's the way it went today. All right, so that's the correct answer.